been neglected. Okay, so ladies and gentlemen, we're going to fire up AnyLogic, the software that we'll be using through much of the term, and we're going to use it to open up an example model. Within this term, in case after case after case, you're going to be building your own models. But today, we have a simpler task ahead of us, which is modifying an existing model. And we'll be taking a look at what these models look like, the sorts of things that they can do. So ladies and gentlemen, I'd like you to go to Help and select Example Models. Okay? And I'm going to follow this as I am wont on my screen. Okay? And I'll try to size my screen as per the magician's request in visible areas of my desktop here. Alas, my not quite perfect, but there we go. Okay, so ladies and gentlemen, if you come up and you see this screen, you're in good shape. Otherwise, you can do this. And there's this example models here area. Okay, and I'd like you to go now. Having done this, you can go down to the How-To Models area here, and I'd like you to scroll down on the right-hand side. So over here on the left, you have to go to How-To Models, and scroll down here on the right-hand side to SIR Agent-Based. You'll see that there are dozens of models, some of which I might note originated in this very building that accompany the software package. And I'd like you to scroll down on the right-hand side here to SIR Agent-Based. The cavalry has arrived, I'm pleased to announce, and additional machines are being distributed even as we speak. And Seth, perhaps you could help. There's some people having trouble logging in with passwords. They're not sure for what account they're being asked to deliver a password. That's great. Thank you. And in the greatest of indignities, unfortunately, the vaunted tech staff have been turned into TAs for this course, and I'm sorry for the indignity. Okay, so we're going to go down here to SIR Agent-Based, and we're going to click on it. Okay? Boom. And ladies and gentlemen, when that model opens, we should see something like, now in this case, I have corrupted it with some additional settings, so forgive me. I'm just going to go here and eliminate some items here, so you see exactly what I see. You should see something like this, okay? Like this. There we go. And I'm going to close all of the other models, okay? Close others. Boom. There we go. So you should see something like that. Do you folks see that? Okay? Okay, so folks, this is a model that's going to depict some dynamic hypothesis about the world. It's going to depict a sort of virtual world where we're positing certain simple rules in effect. And we're going to see the logical implications of those rules play out as we run a simulation of this model. We're going to simulate it step by step by step over time and see the consequences, the logical consequences of these rules. So ladies and gentlemen, let's go take a look at what's going on here. We see before us, here over on the left-hand side, several pieces of this model. Okay? One is called main, and we're going to come back to this recurrently. This is sort of depicting an environment in which agents are circulating. We have this thing called person, which is going to depict personhood. It's going to depict what it means to be a person in this model. Models, I argued last time, are like maps. All maps are simplifications of the world, and you use different maps for different purposes. Merlin uses a different map to identify the source for electrical problems in a cabinet like this than we would use to navigate through the U of S. Models, like maps, are simplifications of the world, and they're specific to purpose. Here, we're going to provide a sort of theory of personhood for the sake of this model, and we're going to run it out over time and see the consequence of that theory. So let's go double-click on person here, and you're going to see something like this, but you're going to see something like what's on the right-hand side here. So here we have what's called a state chart, which is going to be describing a set of states into which a person can be, the current situation can be classified. Here there's what they call susceptible, so they're subject to infection, or they're infectious, or they're recovered from infection. And then there are these set of processes that move them between these states. A process of infection that brings them from susceptible to infectious, a process of recovery that brings them from infectious to recovered. So this is kind of a theory of personhood. People are also associated with a color here. People comfortable with this idea? This is sort of personhood in our model. I know it's an imperfect representation of people in the world. We don't have their height, their hair color, whether or not they have a mustache. But we have a simplified version of reality. We're going to see the consequence. And then, ladies and gentlemen, we have main up here, which describes the environment in which those people will circulate, sort of the stage in which they'll strut, and then an experiment. And let's run this experiment. We can right-click on this and select run. And when we select this window will pop up, which might allow us to change settings. For example, how quickly the model runs, whether we want it to run little bit by little bit or all at once. For now, ladies and gentlemen, I'd like you to click on this button here, and I'm going to tell you what you see. Here you see in yellow a set of people in a population, and I'm going to pause this for a second. And those people those shown in yellow are susceptible; they're subject to infection. Those in red are those who are currently infected, and those in gray are those who are recovered from infection and who are, for now, this model depicts a situation where we assume these are perpetually protected from infection. Marlon, we have some, sorry, Marlon. So here we have a situation where we've introduced infection at one point in the population. We'll see where that is in the model. And we see something happening. Ladies and gentlemen, given that yellow is susceptible, the people are yellow and they're susceptible, subject to infection. And then through a process of infection, they become, remember this is what I was showing you earlier, through a process of infection, they become infectious, and then a process of recovery, they become recovered, and their color changes accordingly. Given that that's what's going on, can anyone describe here? What before you? What's going on at an informal level? Okay, there's a moving front, a front whose shape is roughly described by sort of a part of the circle here. And that's a front of what? What are all these reds up here? They're people who are infected. So they're people who are spreading the infection. Outside of it, we see a set of what? Susceptibles, and inside, recovered. So we see this kind of expanding front. Expanding in which direction? Outwards, right? Outwards from that source of infection, and it's expanding out, right? Here we go. Spreading out, spreading out. Now, we see a number of features of this situation. And I'm going to just pause it to draw attention while not losing the ability to do something here. One feature is that there's kind of this mottled character of the space in here. What is the fact that one of these is red mean? It means they're still infective, even though those around them are gray. And I'm going to tell you, people spread infection here to their neighbors. So each person has 8 neighbors: north, south, east, west, northeast, southwest, southeast, and northwest. Those 8 directions, the 4 cardinal directions plus the 4 other, and they spread that infection to their neighbors. If they're infected, they spread it to their neighbors. So let me ask this, folks. This pattern you see before us, this ring of fire, as it were, where does that lie in the model? Did anyone see it as I was poking around? Where's that in the model here? Is it in here? Does it say there's a ring? What is it that determines how quickly that ring spreads? You think it's in color? What? I'm being a little bit facetious, but I'm trying to emphasize a point here. What is it that is saying in this model how quickly this is spreading, or saying that it's it's a circular ring here. Where is that dictated? Is it associated with this thing here? Does it say it's a big ring that's expanding at 10 distance units per time unit? Where is that dictated? Yeah, I heard a key word. It's a complex interaction of different features of these models. These components of the model are interacting to yield this behavior. This behavior is what we call an emergent property. It's in no way presupposed. It's in no way built directly into the model. It's in no way presupposed by the model. It's in no way fixed by the model. We can use different words to describe it. But this shape here, and the fact that it's expanding outwards, and the fact that it's yellow outside and gray inside, is not directly set into this model. It's something we told it. We didn't program in an equation that said how big this ring is over time. That, ladies and gentlemen, is in fact something that results from the interaction of these different components of the model. I talked about complex systems not being merely reducible to the parts, in that study of system science being in some sense the study of the whole. Well, this is an example of that. We have a system composed of many of these agents, just like you could have a set of cars on the road, and we could have phenomena, like we have on the road, traffic jams that are in no way reducible to one car. It doesn't make sense to talk about traffic jam in terms of one car. And so it is here. We have these phenomena, these sort of wave fronts, and these patterns that we see in terms of the wavefront moving out that are in no way directly reducible to these pieces. Instead, they're a result of the interaction of these pieces. Now, we're going to experiment some with this model. We're going to be modifying our assumptions some and seeing the consequences. And I want to make a note of that. It's important, this fact that we can conduct experiments using a system like this with ease. Much easier than we could do in the real world. We could take 256,000 lab rats and put them in a big matrix and infect one with influenza and see it spread. But it would be neither ethical nor particularly practical or feasible as an experiment. Among other things, they'd probably interact and bite each other and start running all over the place. But we can do experiments here in silico that are quite easy. So ladies and gentlemen, I'd like to use this as a platform to run some experiments. And we're going to see how we can use these models to ask what-if questions. You have the simplified version of the world. What is the logical implication if we were to make this assumption with it or that assumption with it? What's the logical implication? That plays out in a way that it can never do in our heads directly. We can think through the consequences of our assumptions in terms of the overall behavior much more easily in silico. Does that make sense? So let us, ladies and gentlemen, compute. Let us go pursue that. Okay? So, ladies and gentlemen, I'm using this as an introduction to AnyLogic, and I want to orient you to a couple things here. You'll notice that up here, you can use these various controls to speed up the model and to slow it down. For example, pressing this here will let it continue. You can pause it with this. You can also set the speed of it by turning into virtual mode or slower mode where you can set the speed. So you can actually watch it in slow-mo. You can watch it go very slowly or you can speed it up to see it go in a faster way. If you really look closely here, you'll see the occasional event. Occasional things changing on this periphery at 1/25th speed. By contrast, we could speed it up and we'll see it now spread in a more macroscopic fashion. So we can control the speed of this model. You can also down here go set the model to show you time, for example. So I'm going to go up here and ask it to show the model time, and you can see that it's counting up in terms of the time. Okay? So a little challenge here, folks. A little challenge for each of you. I'd like you to go, we just closed this model. I closed it by clicking in the X in the upper right corner of it. You can also do that by clicking on the down here on the console. There's a little red button, or there's a red button on the simulation. So, ladies and gentlemen, I'd like to go back and run that again, but this time I'd like you to show time. How do I get it to show time? Who spotted the actions I undertook earlier to get it to show the time? What do? I click this small thing here. Of course, soon you folks will be responsible for this, but you should be aware of these features because they're very useful. You click here and you can select model time, okay? And then it will show the time. How did I do that? I clicked on the golden triangle. And then I selected model time. Okay? Are folks following along? Okay? Questions yet? We're gonna be working together with this for a fair bit of time. So if there are any people that are really stuck, just let me know and I'd be glad to help. Okay? Question? No? Okay. Okay. So, ladies and gentlemen, I'd like you now to run the model and see how quickly it reaches the endpoint of the simulation. The boundary, the upper boundary. How quickly does that periphery reach the upper boundary? And I'm going to pose you some questions during this. Ladies and gentlemen, we're watching the time here. We enabled the time. We're going to see how quickly it reaches the upper boundary. But while it's going along, maybe you could tell me, why does this look so ragged? Surely it's sort of part of a circle, but why does it look so ragged here? Anyone? Anyone want to hazard a guess why it's so ragged? It's random. There's randomness. So it hits the boundary about time 300. Make note of that. But you'll notice there's a fair bit of randomness. There's stochastics. There's uncertainty associated with this model. Uncertainty over time. You can notice that it's kind of there's some people still infected in here, and the vagaries of who happens to get infected in this periphery will differ from run to run. There's uncertainty associated with this model. And as we'll see, there's uncertainty about how quickly people recover, to whom they send messages if they're infected, and all these things affect this kind of raggedy nature of the simulation. Sometimes in modeling we seek to numerically capture situations we see in real life. Sometimes we seek to capture the phenomenology, the kind of behavior you see in the real world. We may want to simulate water and the flowing of water, for example, the appearance of water atop a river. And we're not seeking to exactly predict where each wave is going to be on the South Saskatchewan River. Instead, we're trying to capture sort of its qualitative character, the undulations of it. And so it is with these models. Some of them are more stylized and just trying to capture qualitatively the nature of the situation, and sometimes they try to capture very precisely. Ladies and gentlemen, so this little simulation here is characterizing the consequence of some simple assumptions. Let's walk through those assumptions a little bit that are being characterized here. Let's see how it captures them, and then we'll run some alternative experiments, okay? So I had mentioned here that people move from a susceptible state to an infectious state. And they move according to some process. In this case, the process is triggered by receipt of a message. There's actually going to be a message by which one person infects another. That's how the agents will interact, by sending messages, okay? There's going to be a process of recovery, and this is going to be also dictated by a transition. You notice this is called a transition. But here, this is going to be associated with a certain rate, a chance per unit time, say 10% chance per day that you recover, okay? And up here, there's going to be another process associated with infection. And on your version, it may be a little bit different than mine because I may have made a modification here. But in mine, it says send to random neighbor. I think in yours, it may just say send infection, comma, random connected, something like that. but in mine I've made it a little bit clearer. Okay, so folks, here we have a connection where something's going on periodically. As long as someone's infected, they're sending these messages to their neighbor saying, you're exposed to my infection and you should get infected if you're susceptible. Okay? Sends off these messages. And if that person next to them who gets that message happens to be in a susceptible state, they'll become infected. So this is kind of a little theory of how infection spreads. You notice it's sending it to a random neighbor. So it said send infection random _ neighbor, I think, for your models. That's basically indicating a neighbor, one of 8 neighbors. Okay, and we'll see where that lies. So this is a little theory of infection. A little theory of infection. Let's modify our assumptions about this theory, shall we not? We shall. So, ladies and gentlemen, this last item here on the list to the left is something called simulation main. Okay? This is actually, it's denoted with an X, and it's actually indicated in experiment. Okay? Let's add an experiment. Shall we? Let us do so. So I'd like you to go up to SAR agent based. I'd like you to do new experiment, and I'd like you to select a standard simulation, but I'd like you to call it a brief infection. Okay? Brief infection. So you selected simulation, and I'm going to say brief infection, and then I'm just going to say finish. Okay? Here. How did I do that, ladies and gentlemen? I went up to, there's several ways you can do it. One way is you go click on this project at the top, you do new experiment, and then you say brief infection. Okay? So up here, new, right click on this. So it's right-clicking on this guy and say new experiment, okay? And you say brief infection, okay? And then finish. Are people okay with that? Any questions? Okay. So we're going to create a scenario and a sort of a what-if alternative situation where we are going to vary our assumptions about this model, okay? We're going to vary our assumptions concerning the model. And you'll notice that up here in main, there's a set of assumptions encoded about, for example, the illness duration or the infection probability, etc. And you'll notice in main, it by default assumes that the average illness duration is 15, and if you go to simulation, it says average illness duration 15. Okay? So for brief infection, I'd like to change that, ladies and gentlemen, to 10. Okay? People okay with that? So you get to 10. Ladies and gentlemen, riddle me this. How will that change things? People recover very quickly. Maybe they recover quickly because we're simulating an intervention. We go out and find people actively. Maybe we screen people in the population for illness, so we bring them in for treatment quicker. Maybe it's a treatment-mediated recovery. Maybe it's a situation where we're just assuming that we're dealing with a bug from which people recover quicker. Maybe we assume people have better education about how to take care of themselves and can recover from a bug which just takes a bit of care on their part, rest, etc. In any case, we're going to assume a briefer infection of 10 days rather than 15 days. Okay? What would the implications of that be in terms of what we've seen? How visually would it be different?
The red band will be thinner, smaller.
Okay, the red band will be thinner. Will it make a difference for how quickly that infection moves? After all, each person is going to be infected for less time, so maybe they infect fewer people, and so it won't move as fast. What do you think?
It'll have a tiny impact, perhaps.
Maybe a bit of an impact, okay. Okay, so Will it make a difference for how quickly that band reaches the top? We timed that earlier. Well, there's no use purely depending on it's good to sort of think these things through a bit. What am I expecting? But we can check this very straightforwardly, right? We can run it. So how do we run something here? We can right click on it and do run. Another way is you can do run up here by choosing it from the list here. You can also do it from this menu over here, this model menu, run. Ladies and gentlemen, let's do brief infection here, okay? And let's see what the consequences are. Okay, now you'll notice that it's actually complaining a little bit bitterly down here. We actually have to be a little bit careful about this. This is unfortunate, but it's actually a little bit memory constrained. And mine, at least, it's getting this red indicates it needs more memory. Here we see it starting to spread. It's just slower. Okay, I'm going to speed it up here. So what are we seeing? It's actually started at a somewhat different position here. I'm going to run it flat out. Okay. There we see, and broadly it meets some of the criteria. It's a thinner band on the outside, but we're still memory constrained here. I should have done something a little bit more artfully here. We'll see how to fix that in a minute. So ladies and gentlemen, we could time it, and unfortunately it started at a very different position. I was hoping it would start down there, as it often does. The answer is it wouldn't make that much of a difference for how fast it moves. It's actually a very minor difference. Ladies and gentlemen, there seem to be fewer sort of dots in the center here. Why is that? They recover faster, so there's fewer around. Fair enough, so people are recovering faster, and we see it moving out here. Let's go fix this problem. Is this afflicting you as well? Is it troubling you? Let's go see how to fix that. I should have been more artful. Normally I sidestep that issue through a sleight of hand, but let's go stop this. How do I stop it? Well, one way is up here. You can do that. Another way is by clicking this thing as a whole. Another way is to go to the main simulation window and clicking the stop model up here, or it's down in the console. Okay, ladies and gentlemen, does anyone, by the way, recognize this environment? Have any of you seen this environment that lies before you? What is it called? Eclipse. This is Eclipse. This is none other but a repackaging of some things in Eclipse. And a lot of the things you'll be used to in Eclipse, like code completion. Okay, so you will find this a familiar. That shows a star there, indicates that it's been changed but not yet saved. You know, this sort of hierarchical organization. Those who have worked in Eclipse before will recognize this. Okay, so let's go figure. Let's go fix that problem with the memory. See where it says maximum available memory? Change it to 1024 from 256, okay? 1024. Boom. Okay. I like to add sign effects to my models. Okay. So if you change it to 1024, this model will actually run a lot faster. That's just giving it more resources to do its job, okay? And I'll run it. What did I do? I just, when I selected this brief infection, I changed maximum available memory in the properties window. Whoop! Those properties allow me to see the properties for the thing that's selected here. If I selected a button, it would show properties for that button. If I show the experiment, it will show properties for the experiment. And we're going to set it to 1024. People okay with that? Okay, so I just ran this thing, and I'll speed this up. Tell it to go its fastest speed, and now it's going gangbusters. And look, let's see how quickly this gets up there. It seems to start at roughly the same place, and maybe there's a little bit of difference in speed, but it's pretty similar. You notice now it's at time, it says infinity. It's smart. It knows there's no more work to do. Done as far as all the things that can possibly happen. Okay? Okay, ladies and gentlemen, and we'll talk about how that is. There's an event handler, an event scheduler going on under the covers, and there's no more events to be handled, so it thinks it's done. Okay, so this is a brief infection. We asked a what-if question here. We posed a counterfactual. We asked, what if this were the case? What if, suppose we had a brief infection, what would the implications be? Let's continue that line. Let's make a really brief infection, okay? Let's make one, well, you tell me, how do I do this, ladies and gentlemen? I want to create a very, very brief infection of length 5. How do I do that? Okay, good. What do I have to do before that? I need to create a new experiment. And how do I do that? We can do it through the file menu, new experiment, or we can do it by right-clicking on the project. I'm going to call it very brief infection, okay? And we'll set this to be, we'll create it, oh, very brief. It's not a cheese, it's a brief, okay. We'll set it again to max available memory 1024, and we'll set this average illness duration. Let's set it to actually 3. Okay, ladies and gentlemen, what do you think the consequence of this will be? A very, very brief infection. What would we see? A thinner band yet, maybe? Would it impact the speed at which it travels? Would it go a lot faster or slower? Maybe not? Okay, a bit of uncertainty. Let's run it. Anyone have a different theory?
Not everyone's been infected.
Okay. Okay. So that's interesting. Okay, so what's going on here? What lies before us? What mottled surface? Can anyone explain to me what's going on?
Patches of uninfected people.
Patches of uninfected people. Okay, let's try that again. Do you think those patches are always in the same location? Not quite, right? They differ a little bit. Okay. They exist in sort of whole patches. I mean, they're not totally disconnected either. It's not just like we threw down in a Poisson point process, threw down a bunch of dots on it. They actually cluster because there's certain areas that are spared from this prairie fire raging out from the center. Yes?
First time I realized that it was where like one great big
Indeed. And I had a devious goal in running this many times, and that was, well, not devious, but I had an ulterior motive, which was to show you something that this gentleman encountered. So this gentleman, and your name? Braden encountered something. He saw sometimes that there's a square like that sits before us. What's going on? The infection was never able to spread. Just by the luck of the draw, this very first person, this index infected, this initial person, that initial spark that settled on the prairie went out before it could ignite a fire. This initial person did not infect anyone else. Just by luck of the draw, they were able to recover before they infected anyone. So that too is a possibility. And if we lowered it from 3 days on average to 2 or to 1, we would see this more and more likely. No infection at all. Qualitative difference, a phase change in a way. I mean, we see the difference between water and ice almost. We see that intermediate state, there's actually a state with these sort of blotches where it doesn't even infect people. Ladies and gentlemen, these are things we might have imagined if we sat back and thought long and hard about it. This is a very simple model. But a model can help make these things more precise, can help reveal to us these patterns that might have been, incomplete and unsure in our heads. We didn't have a fully consistent understanding of what the implications were. And we could run this on this model in these simulations, right? Does that make sense? Okay. So ladies and gentlemen, I'd like you to run one more experiment for me, and then we'll do something more profound. So I'd like you to add in your experiment in, And we're going to make this a prolonged infection. Prolonged infection. Okay? Okay? So how do we do that again? We could do it through File, New, Experiment, or we can do it through by right-clicking on this thing here. But we want to add this in, okay? And by prolonged, we're going to set this to maximum available memory 1024. That's all about the plumbing, and I apologize especially to those not from computer science, but we need to sometimes give it enough resources to do its job efficiently. And then average illness duration here, I'd like to set it to 75 time units, okay? Okay? People okay with that? 75 time units. Okay. So this will be days. We can actually go set where the time units are, and in fact, if we go to the model here, up at the top, this model is actually built in a different version of AnyLogic, but you know, in mine at least it says days. Does it say days for you? I looked at the model as a whole, and it's set to days as the time unit. That's just our yardstick for time. That's just how we happen to measure time. So when it says 75, what is it? 75 days, years, seconds. It'll make a difference if we're trying to keep track of a calendar at which things are occurring. Does that make sense? Okay, ladies and gentlemen. So 75 days. Let's go. So you tell me. Suppose we made it 75. What's going to be visually the difference? What will you see different? I'm not asking anything terribly profound here. A lot more red. Okay. And let's go. Here we go. And we see a thick red boundary and lots and lots of these dots inside. Why is that? Why is it all mottled inside?
Takes longer to recover.
Long to recover, so people stay infected for longer. Okay, I won't go through all the gory details with that, but we're going to come back to those examples in a bit. We've just set it up, and now we're going to play ball a little bit more in a more interesting way. Okay, just set these experiments up. Ladies and gentlemen, I'd ask that you save your model, if you can. Control S will allow you to save it. And now we're going to make a more profound change. Ladies and gentlemen, I've just been talking with you about changing assumptions that are encoded with these parameters. So we're changing parameter values here. We're changing these assumptions in terms of the degree of the situation. How quickly people recover. Is it faster? Is it slower? It's a matter of degree, but there are profound differences in behavior that can spreading infections, spreading out from a center. On the other hand, we saw a mottled surface after the inspection went through, where it wasn't all gray, but it had patches of susceptibles intermixed with the gray patches. And finally, we saw a situation where we could end up in a surface where no infection at all. Just one person recovered, the rest remaining susceptible. These are very different behaviors that can be elicited through just small differences associated with these parameter values, comparatively small. Ladies and gentlemen, though, we're going to now do something more profound. We're going to change our theory in a more significant way, a mechanistic theory of sort of how what we call the natural history of infection here, how the infection develops. So double-click on person here. And ladies and gentlemen, what I'd like you to do is, I want to imagine a situation. So now we have people susceptible, infectious, and recovered, where, again, people start, they're subject to infection, hence susceptible, they're capable of being infected. They can then become infectious. They can spread the infection, hence infectious. Other people will call it infective. And then they become recovered and permanently immune right now, right? Why do I say they're permanently immune here? Why do I say they're permanently protected? Because
no state change from recovered to susceptible.
Yeah, you can't get back to susceptible. These are one-way arrows, right? But now I want to represent a situation where we have what I call waning of immunity. You can lose immunity. How would I add that? How would I, if I wanted visually to change this thing so that people lose immunity, it's not persistent, it's not lifelong, it's not permanent, how would I do that?
Add a variable from recovered to susceptible.
Yeah, so we're going to add a transition. So we're going to modify the structure of the model. We're going to modify kind of the mechanisms assumed in our theory to add in now this process associated with waning immunity. We're representing processes here. In some sense, how the underlying world is working. We can look at statistics coming out of those processes, and it's like, in that sense, it's similar to the world, right? We look at statistics coming out of about the number of cars passing this point in the University Bridge over time, or the rate at which the Saskatchewan River flows over time in different seasons. And those are statistics that are generated by underlying processes, patterns of kind of interaction in the underlying world. And some of it is here. We're going to be running this model. It's going to be running these processes, and we can collect data from it over time. Does that make sense? Okay. So ladies and gentlemen, let's add that transition. And now, I want you to pay close attention, because we're going to go to a different area of space. We're going to go to this palette. Now, I think for you folks, this palette may be behind here. You notice that in Eclipse, for those not familiar with it, you can drag windows around. And I think for you, is your palette up here behind projects? Okay, so you could keep it here. Just go click on it. Or you may want to drag it down here. And you could have a separate version. By the way, by double-clicking on this, you can also make it full screen. Those of you familiar with Eclipse will know that pattern. Will you not? Yes, it's a very useful pattern. Okay, so go down to palette, and ladies and gentlemen, I'd like you to go down to state chart. It's not the top one, but it's the sixth one down. It looks like a little line going into a yellow square. And I'd like you to click on that, okay? There you go. By the way, I don't know what they're teaching exactly in 270 these days, but have you folks seen state charts before? UML state charts as part of 270 perhaps, or maybe 370? 270? Okay, yeah, so that's a very familiar mechanism for those from computer science background. Okay, so ladies and gentlemen, I'd like you to drag this transition over to this window. We're going to add a transition from recovered back to susceptible, okay? And don't be too worried about the aesthetics, just where it's going, from whence it comes and whither it goes. From where it comes and to where it goes. So drag in transition, and you'll notice when I'm dragging it, I click here and I drag, and I'm dragging it until it comes out of here with a green thing here. No. For this very first class in exposing you to the software, I'm teaching you the basics. Naturally, I'm not through this course going to be doing this level of detail, but I want you to start getting familiar with the software at first. There's thousands of videos you'll find me talking, about 1,000 you'll find me talking about this stuff online. So if you want to see me talk about clicking and dragging, you can do that. I'll be happy to oblige in my virtual self. Okay, but we're going to use the class for some more substantive things. But I want you to get familiar with this. So you drag in, and you get it to click to sort of go from this point, and then we're going to drag up here. Okay? So how did I do that? I dragged in here so that it was coming from this. It came from, whence did it come? From recovered. And then I dragged the other part of it so it went up here. And make sure it turned green at each point to indicate a solid connection. Okay? Okay. Thank you, Richard. So now we have this arrow back, this transition back. So we can lose immunity and become susceptible again. Now, I stand before you as an engineer. I stand before you as an engineer whose sense of aesthetics are weak, except in certain engineering domains where I have vociferous aesthetics associated with code quality, for example. but visually I have weak aesthetics. But even this grates on me a little bit. So this grates even upon me. So I'm going to double click on this and drag it out so that it's clear it doesn't actually intersect with that. Okay? Functionally, we've made no difference. It's just clearer. To someone looking at this diagram, the aesthetics that trouble me are the aesthetics associated with, particularly with function, because if someone can misunderstand it, it troubles me. It worries me. I see the danger, and I want to act to eliminate that danger. And the danger here is if someone saw that error go through this, it might think it's going back to infectious, when really it's just a pass-through. So it's clearer if you drag it out. And visually, it's a little bit nicer. We've prettified it as well. So you can go click on this, and you can see it as you see fit. Okay. So ladies and gentlemen, we're going to associate this timeout transition, and we're going to associate it with a timeout of 75 time units. Okay? 75. So you'll notice that we're associating semantics with these transitions. This transition was a message transition. This transition here was a rate transition, a certain chance per unit time. You have a certain, like a 10% chance per day of recovery, for example. This is a timeout transition. It occurs after exactly a certain time, where that time it may be set precisely, or where by a fixed number, I should say, or you may draw it from some source, a database, or from a random number or something like that. Okay? Are people comfortable with that? Okay. Ladies and gentlemen, so we've just altered our theory. This model captures a dynamic hypothesis, a sort of theory of the world. It has dynamic implication. It simulates it over time. What, ladies and gentlemen, do you think the implications of this altered hypothesis, this altered theory will be in terms of the behavior of this model? Suppose we were to go run the default scenario here with this altered model. By the way, who needs help? Does anyone have a question of what I've done here? All I've done is I've dragged this transition over here and I've connected it up from recovered to susceptible. Ladies and gentlemen, can anyone tell me what would the implications of this be? So if we can have people recovering now, what's going to be the implications for what we see, for those emergent properties?
More like a bubbling back into itself.
Okay, so some sort of bubbling, some sort of kind of recurrence of some phenomena. Okay, so I like what I hear. Here, ladies and gentlemen, let's run this. So I just ran the default simulation, and what do we see different? What do we see different? Okay, we have a wavefront like before, but now we have multiple wavefronts, right? And why? And moreover, we almost have multiple generations here of wavefronts. A first generation, a second generation, third generation wavefront. Here's a fourth generation in the offing. Ladies and gentlemen, these wavefronts, can anyone give a sort of give a qualitative explanation, a rough explanation? What are we seeing here? Why do we see these wavefronts?
The people who get infected first become susceptible again, but there is a chance that there's still people in that population that are infectious. So they get infected again and they ignore it.
Yeah, okay, so we had a kind of initial set of susceptibles who got infected from this first wavefront. And they remained infected for a while, then they recovered and they started to become susceptible. But there's enough people around here who have remained infective that when they recover again, when they again become susceptible, they can get, so when they become susceptible, when they lose immunity, they can then get infected again, right? So we have these kind of generations of infected. So, like in this interior wavefront here, I've lost track of the count here, but these folks may have gotten it, like a given red person here might have gotten infected, what, 4 times now? This might be their 5th time around. So we can talk about generations of infections here, or generations in terms of kind of these wavefronts, right? There's kind of the first generation of infection, the second one, the third wave, to use the term wave of infection, right? These are, the thing I want to draw attention to, folks, these are very real patterns. These are very real regularities. They're structured, they're ordered. They're very, very real types of things. But ladies and gentlemen, they're emergent properties. They're not in any way directly built into our model. There's nothing about waves of infection here directly. There's nothing about, successive generations. There's nothing about wave fronts and about propagating outward that we programmed into this model. This is resulting in this extremely complex pattern here is the result, ladies and gentlemen, of the fact that we saw this transition from this kind of single wavefront, for example, to this complex pattern. That's a result of adding a single transition. A small change to that assumption about how things work can lead to a profound and very, very textured, very interesting, and multifaceted sort of implications for the real world. There's a lot of complexity here, but there's real structure. We can label these things, these emergent patterns, and talk about them in very meaningful ways. Waves of infection, just like we can talk about the traffic jam that occurs every day on the University Bridge, going into town. These are real things, but they're emergent. They're resulting from these lower level processes interacting in complex ways. And if we wanted to change these things, if we wanted to eliminate, the second round of infection, or we wanted people to never get infected in the first place, now we're needing to reason about those underlying processes that give rise to these. If we wanted to change how quickly these move, so we had quicker time to prepare for the next epidemic or the next outbreak, we would need to reason about the underlying system. We need to reason about what's giving rise to this to change it. Does that make sense to people? To really change it in a reliable fashion, to be confident we're going to change it in the right way, we're going to need to reason about the processes that are giving rise. So ladies and gentlemen, let's look at this a little bit more though. Let's go back to our model. So I just ran the default case. Suppose we ran the brief infection case. What would the implications be for that? Anyone? Well, let's go in the right order. How about very brief infection? What would very brief infection be? Very briefest. What do you think you'd see? Sometimes you'd see just one person. There we go. Right? There it's going. Okay. Let's speed it up. Right? What do you think we'll see, folks? What do you think we'll see? What are we going to see in 2 minutes? Why? There's not enough infectious people still around to infect that next wave of people who have now recovered from that first infection. And it spread. It spread through the population initially. Maybe not every single person, but it spread. Oh no, this one didn't even spread at all because it never caught hold. Let's do it again. Okay. There we go. And there's no one still infected. This is very brief infection. So they recover from the infection very quickly, and there's very few of them around by the time there's very few infectives around by the time people are starting to lose their immunity. Here are the folks losing their immunity, these yellow in here. And where are the infectives? They're all further out, right? So they're never ne'er the twain shall meet. These ones aren't interacting with those ones. Does that make sense? So we can talk again about these higher level quantities, the waves of infection. The first wave infectives never touch the sort of second wave of susceptibles, right? But These are resulting from this underlying process. Okay, so that's one case. How about for the brief infection? What do you think will go on there? Okay, here's brief infection. And I hope you folks are realizing the limits of kind of, we can reason about these things some in our heads, but there's a lot of guesswork and piecing together, and frankly, we're not very good at thinking through the logical implications. Okay, we have exactly 10 times to recover, and the average time to recover is maybe 10 days, and we have and then we have a waning time of immunity of 75 days exactly, and how likely is it that one will infect the other? Instead, the most reliable way to do this is to simulate it over time. And here we see, it is just enough time that there are some of these infectives around. It could even be a bit longer. So here we're getting these second waves. Now, if we run this thing long enough, what do you think will happen with the stochastics? Well, eventually, actually, we'll go entirely susceptible again. Just by the luck of the draw, it will go without an infection. It's very unlikely. We may run it for hundreds of years without that happening, but eventually it probably will, through luck of the draw, be in a situation because of the stochastics. But there are enough around that by and large it does infect. So here we get a kind of different qualitative feel to it. We have these sort of quite distinctive bubbles, as was used before, a quite nice evocative term. Okay, ladies and gentlemen, what if we now were to examine the case of a prolonged infection? This would be the last scenario we run. How about a prolonged infection? How would it be different? Help me think this through. Sorry? Yeah? A lot more red, and therefore the generations are less distinct. Where are people? Do you see anyone losing immunity yet? Oh, yeah, there they are. I can see them. Can you? They're in there. They're in there somewhere. They're actually in there. There's a slightly higher density area here. Higher density because some people have become recovered and sort of lost immunity and becoming infected, but you can barely see it. Can we really talk about generations of infectives here? Not so easily. A little bit, but they're not well separated in space. They're not really well delineated spatially. So here we have this process. It's a process operating over time and over space. We can articulate theories. You can actually see it from where I am. I can see on my monitor. There's actually kind of a low density region here and a higher density, but it's not really nearly as well defined. So different, quite distinctive different patterns from different minor assumptions, and then we get major assumptions in terms of how our theory of how infection works in this population. So we have here this theory describing a process in space, a process in over time. We haven't gone to all details. We'll be leaving that for later for online videos. But the important thing is to realize that we're characterizing these underlying processes in the world, and out of them come these statistics, these information on the number of infectives over time, for example, etc. We have here a sort of theory operationally captured in a model. By operationally here, it means we can run it in this case. We can run the theory and see its consequences. It's not merely a theory on paper, which is kind of loosey-goosey. It's a theory that's quite specifically and precisely articulated. Precise, I don't mean necessarily it's accurate, but it's exactly specified. And we can run out and see its implications with different assumptions, say about parameter guys. And we can vary that theory. We can add in these these assumptions about whether people lose immunity, etc. And I would argue to you folks that just by articulating a theory like this, articulating a theory for some sort of real-world situation, this is of course stylized, but if we have a real-world situation, being able to articulate this is a contribution, because it puts it out there in the public domain. It takes it out of our heads about what we think is going on. It makes it transparent, makes it explicit, so that others can look at it, can question it, can probe it, can critique it, can refine it. They can modify it, they can test it against their data, for example. So creating these models they're thinking tools. They help us think through the consequences of our assumptions. But they also, ladies and gentlemen, provide a way for explicitly characterizing our theories of the world in a way that can be shared, critiqued, refined, challenged, modified, built on. Does that make sense? Okay. We've also seen, and in a point we'll come back to several times, that in the packages we'll be using here, we can actually characterize the what of we're describing in a way that brings it to the forefront rather than all the details of the how. There's lots of details of the how, and we'll talk some about those in the course of this term, about how this is being simulated under the surface. But a lot of what this term is about is kind of building these models, the art of building these models. And here it's useful to keep the description of what we're characterizing. There's a sophisticated system that turns this, that unpacks this in a computational way so it can actually get simulated in an efficient, rigorous, correct way. And we'll talk some about the event scheduler that lies underneath it. But it's a benefit. It's a great benefit that we can describe these models visually because it makes them more easily comprehensible. It means that if we're dealing with people who have never built models themselves or are not computer programmers, they can still know something about what's being posited here. And they can, just by glancing at something like this, they can recognize, for example, oh, you're not assuming any waning of immunity. And they could suggest that you put that in. And the sort of work I do, I work with doctors, those who are experts in public health, epidemiologists, and they can do exactly that. They're not familiar with AnyLogic. They don't work with all the details of this. But by seeing my state charts, they could say, you know, I think you're missing a state, or I think you're missing a transition. And that's really valuable because you can get feedback. The model becomes a boundary object, as we say. It becomes a point of common discussion where each of us in our own disciplinary vernaculars can come together and talk in common terms about something shared. It's kind of like being able, if you're learning a language, being able to take an object, you describe it, someone else in a different language describes it, you know what each of your terms means because you're talking about the same thing. So, you know, you can point to blue and you can put to green, and each of you says your respective words, and each will know what the corresponding word is in the other language. So it is with models. So we've taken a glimpse of models. This is what this course is about. It's about these emergent patterns. It's about building these models. It's about articulating these mechanisms. It's about using these mechanisms of modeling to build up our descriptions of the world and to see the logical consequences writ large of those assumptions when upon the broader behavior of the simulated system. And it's about being able to take those simulated systems and analogize them to what's going on in the world and to improve our models to make them more representative or make them more responsive to our questions about the world. So, ladies and gentlemen, we are out of time for today. But I hope this has been a useful little exercise. I recognize that it's been painful. We moved to a new room. Not all of you had machines. Some of you haven't received the serial numbers for your personal machines. There weren't enough lab machines. I thank you for bearing with us. We've been struggling to deal with this situation with the projector. I was assured that this room would have great ways to project, and I can't even hitch up my laptop right now. So thank you very much for bearing with us. We're going to try to improve this, get more lab machines next time. I hope you benefited from having these plugs. Is everyone's plugs worked okay? because they're still not done with this room, it turns out. And I was afraid that some of the plugs might not work. But I think if it's okay, we'll meet in this room for the balance of the term then. And we'll just bear with this. I'll bring a projector for as long as I have to. Okay? And I will send you some suggestions. I meant to post the projects, but I'm still waiting a bit of feedback from some people on project ideas who want to propose them for the class. So I'm going to try to do that within the next day, and I thank you for your patience. And I will see you, ladies and gentlemen, on Thursday, where we'll dive into the first type of modeling, system dynamics. Thank you very much. Oh, terrific. Those who have lab machines, maybe if you could just put it on the cart over there, I'll follow you real tomorrow. Okay? Thank you. Yes.
I don't know how to use this.